In this video, we're going to discuss judgment and decision making. Here are some key terms described in your textbook. According to the bounded rationality framework, human beings try to make rational decisions, but our cognitive limitations prevent us from being fully rational. Time and cost constraints limit the quantity and quality of information that is available to us. And we only retain a small amount of information in our usable memory anyway. Limitations on intelligence and perceptions constrain the ability of even very bright people to make the best choice based on the information that is available. This line of reasoning has led us to research the systematic and predictable biases or mistakes that influence judgments. But before we can identify the limits of rationality and how biases manifest, we first need to identify exactly what a rational decision-making process would look like. According to some scholars, a rational decision process would follow these 6 steps. Let's say, for example, you're accepted to several graduate schools and you need to decide where to go. How would you go about picking the right program? Step 1 in this sequence is to define the problem. In this case, selecting the right graduate program for you. Step 2 is identifying the criteria necessary to judge the multiple options, their location, prestige, faculty, etc. Step 3 is to weigh the criteria. In other words, out of all the criteria you identified in step 2, ranking them in terms of how important they are to you. Step 4 is to generate the alternatives. In other words, the schools that you were admitted to. Step 5 would be to rate each alternative. In other words, rate each school on each criteria that you identified. And then step 6, computing an optimal decision based on your own ratings. Now we're going to do an exercise to illustrate some of the biases that we have. And I'm going to ask you to pause the video as soon as I give you the instructions. Listed on this slide are 10 uncertain quantities. Do not cheat. Don't look up any information based on these items. For each of these, write down your best estimate of the quantity. So, for example, the first one is the first year the Nobel Peace Prize was awarded. So you would have to write down a year. But for each of them, I want you to also add a lower and an upper bound around the estimate, such that you are 98% confident that the actual correct answer would fall within that range. So for example, if I wanted to know someone's weight, I could estimate that they weigh 160 pounds, and that I am 98% confident that they are somewhere between 130 and 200 pounds. So now go through that process of identifying the 98% confidence interval, the upper and lower values for each of these 10 quantities listed on the slide. You should try to do it for all of them, even if you don't know much about those quantities. I admit myself, I don't know very much about those, but the idea here is to identify errors and biases in confidence. Pause the video now and go through the exercise. I will reveal the answers on the next slide. Okay, here are the answers. The first year the Nobel Peace Prize was awarded was 1901. So in order to get this correct, the year 1901 would need to fall within your range of values. So if your range was from 1850 to 1950, you'd be correct. But if your range was from 1930 to 1940, you'd be incorrect. And now here are the rest of the answers. The date the French celebrate Bastille Day is on the 14th of July. The distance from the Earth to the Moon is 384,403 kilometers, or 238,857 miles. The height of the Leaning Tower of Pisa is 56.67 meters, or 183 feet. The number of students attending Oxford University as of 2014 was 22,384. The number of people who would travel to space as of 2013 is 536 people. In 2012 to 2013, the annual budget for the University of Pennsylvania was $6.007 billion. The average life expectancy in Bangladesh as of 2012 was 70.3 years. The world record for pull-ups in a 24-hour period was 4,321, and the number of colleges and universities in the Boston metropolitan area is 52. This exercise we just did helps us illustrate the overconfidence bias. you went through those 10 quantities and set your range of values so that you felt 98% confident that the answer fell within that range. If you were 98% correct for all of them, then you should have gotten 9 or 10 of your estimates correct. So count out the number of ranges that actually included the correct answers that you chose. If your ranges surrounded 9 to 10 correct answers, then you were appropriately confident in your judgment. But most people who try this only get between 3 or 30% and 7 or 70% of the correct answers, despite claiming 98% confidence that each range would surround the true value. As this shows, humans tend to be overconfident in their judgment. So the overconfidence bias is the tendency to have greater confidence in our judgment than is warranted based on a rational assessment. Okay, next exercise. We know that executive fraud occurs and that it has been associated with many recent financial scandals. And we know that many cases of management fraud go undetected even when annual audits are performed. Do you think that the incidence of significant executive level management fraud is more than 10 out of 1,000 firms, that is 1%, audited by Big Four accounting firms? So you can choose 1, yes, more than 10 or more than 1% in 1,000 Big Four clients have significant executive level management fraud, or no, fewer than 10 in 1,000 or fewer than 1% Big Four clients have significant executive level management fraud. Now, what is your estimate of the actual number of Big Four clients per 1,000 that have significant executive level management fraud? So choose a number yourself and write it down. Fill in the blank. Blank in 1,000 Big Four clients have significant executive level management fraud. All right. Now, this exercise essentially shows what's known as an anchoring bias. In the last activity, I asked you to estimate the rate of fraud for every 1,000 Big Four clients in finance. But before doing that, I also asked you whether you thought the rate was greater than 1% or 10 cases per 1,000 clients. This anchored your response. I could have given you a different number. I could have asked, do you think the rate of fraud is more than 200 for every 1,000 clients? Most people intuitively know that 1% or 10 cases is too low, while 200 cases or 20% is too high. So the estimates will fall within that range. But for those who get the 1% anchor, their responses are much closer to the number 10. And for those who get the 20% anchor, their estimate will be much closer to the number 200. The reason this is considered a bias is because most people are unaware of how these initial numbers anchored them to those values. The anchoring bias is basically that we are affected by an initial anchor, even if it's arbitrary, and our estimates are pulled towards that anchor. Okay, last exercise. In this case, imagine that the United States is preparing for an outbreak of an unusual avian disease that is expected to kill 600 people. 2 alternative programs to combat the disease have been proposed. Assume that the exact scientific estimates of the consequences of the programs are as follows. If program A is adopted, 200 people will be saved. If program B is adopted, there's a 1/3 probability that 600 people will be saved and a 2/3 probability that no people will be saved. Which of the 2 programs would you favor? Pick A or B. Now, here's a slightly different way to frame the problem. Again, imagine that we're preparing for an outbreak of a disease that is expected to kill 600 people. 2 alternative programs have been proposed. If program C is adopted, 400 people will die. If program D is adopted, there is a 1/3 probability that nobody will die and 2/3 probability that 600 people will die. Now, which of the 2 programs do you favor? This illustrates framing bias, which is that we are affected by the way in which information is presented. The tricky part about this exercise is that the 2 pairs of options are identical in terms of their outcomes. In other words, the number of people who will be affected by each choice. But the difference is in terms of framing large numbers of people who will die versus large numbers of people who will be saved. In the first variation, most people choose program A, which guarantees that 200 people will live. But fewer people chose program C here in the second framing because it guarantees that 400 people will die. In the second framing, more people choose program D. The first program was framed in terms of saving lives. Most of us, when we make decisions that are about what we can gain, like saving people, then we are risk averse. So we prefer to lock in the possibility of saving 200 people's lives for sure. The second problem is framed in terms of losses, and 400 deaths looks very bad, so we are motivated to seek other options, even if it means making the riskier choice. Overall, the three exercises we did that show framing, anchoring, and overconfidence are just three of the many biases that affect even the smartest people among us.